Hi everyone, thanks for joining our webinar today. My name is Alessandro Rossetta. I am the CEO and founder of FLIM LABS. And today we're gonna dive into this webinar in which we will talk about our FLIM kit and how, thanks to this new type of technology, we can unlock new applications, thanks to the use of our FLIM Starter Kit. To begin with, I want to spend a couple of minutes telling you that the basic principle that is the state of the art of measuring fluorescence lifetime relies on a technique called time-correlated single-photon counting. Within the context of laser-induced fluorescence, we use time-correlated single-photon counting to basically be able to reconstruct the decay profile of our intensity signal after we excite the sample with a very short laser pulse. So this is, let's say, the technique at the base of our technology. And how this technique work? Well, for implementing time-correlated single-photon counting, we would need a pulsed laser source. Of course, we would need a sample and an emission filter so that our single-photon detector, which is part of our setup, is able to sample the photons, only, let's say, the fluorescence photon coming from our sample. Then we need, let's say, a third element, which is our TCSPC electronics, our data acquisition electronics. And let's say we can also add a virtual fourth element, which is a computer capable of reconstructing the decay profile of our fluorescence signal. So how the technique works? We basically shine a laser light into our sample. This laser light has to be delivered into pulses. We can measure the time of arrival of single photons irrespective to the laser pulse, and then we basically use all these time of arrivals of our photons to build a histogram in a computer reconstructing the decay profile of our in fluorescent signal, on top of which we can measure the characteristic of the decay profile, so the fluorescence lifetime value. Having said that, I wanted to emphasize the fact that the FLIM Starter Kit is a technological solution that we developed specifically for measuring fluorescence lifetime. Is an optimized hardware and software combination with the only aim of providing a unique tool, let's say, on the market, dedicated for measuring fluorescence lifetime analysis. Why is that? Because if we take a look of what is already, let's say, on the market and what has been used for measuring fluorescence lifetime, well, you see, most of the instrumentation that are out there are bulky. They are very heavy. They need to be powered to the power grid. And most importantly, the software, which is used for processing the data, is most of the time a general purpose software capable of dealing with particle physics experiment, quantum experiment, eventually also doing fluorescence. So the idea that we had in mind while developing the starter kit was to conceive something dedicated only for fluorescence lifetime measurement, specifically also designed to meet the needs of today's users, which I would say they would go beyond the lab environment, exploring, let's say, application in context which are, let's say, meant not to be constrained by four walls. And the idea we had was to develop the FLIM Starter Kit, which I am introducing in our webinar today, which is basically made up by a pulsed laser source that you see here. Then we have the FLIM data acquisition card, our TCSPC acquisition module. Then we have our detectors, which is a single photon avalanche diode detector. And of course, we have a software component. As you may already see from this picture, the three devices are compact, meaning they are portable, because the three of them can be USB powered. And this is, let's say, the image with the scale, in real scale, with a laptop which is just 13 inches wide. So if we start to talk and analyze the components of our FLIM kit, we see that we develop picosecond pulse lasers with a peak power of 160 milliwatts and with pulses that can be as short as 50 picoseconds. All these lasers, they are available in several wavelengths, and we have two versions. We have a version that is USB powered and USB controlled, and a version which is still can be powered by with the grid, but can work as a standalone, so no, let's say, software needed. If we continue to talk about our lasers, you would see that these lasers are fiber coupled, meaning that they offer they are a flexible solution for coupling these lasers with any type of setup, of optical setup, either imaging or single point, let's say, type of measurements. Indeed, if we connect a monomode fiber to the fiber receptacle, the beam quality proved to be, let's say, an excellent beam quality with only these values of, let's say, M and divergence asymmetry. And also these values were stable by, let's say, increasing the room temperature to our laser. Talking about the laser, the main function, as I've explained, is to generate very short pulses of light, and whenever a pulse is generated, the laser is capable of outputting a digital signal mimicking, the delivery of the pulses. In this way, for every pulse that we have, we also have, let's say, an electronic digital signal that we can use as a sink for our TCSPC electronics. Diving in a more, let's say, specific function of our lasers, since we've talked about the sync signal, these lasers have an internal oscillator. So they are a unique module comprehensive of the laser head together with the oscillator, but also they allow for external triggering, meaning that we can set the laser to be triggered by an external source, because we implemented what it's called pulses on demand, meaning that by externally triggering the laser, we can command light emission, a pulse emission, pulse by pulse. Now, let me move and talk about the spot detectors. We have two versions of the spot detectors, both of which can be USB powered and both of which are fiber coupled. One that is more blue shifted with a peak sensitivity around 450 nanometer, and a second version which is identical. The only thing that changes is the spectral sensitivity, which peaks x 633 nanometer. Talking about the SPAD, the main function is to detect single photons. So for each single photon input, we get a digital output with a jitter of about 200 picoseconds. So this makes the detector very, very flexible because the output is already digital. So a single photon comes in and a single photon digital output comes out. When manufacturing the spot detector, we thought also of providing a flexible solution. So the metal base of the detector has holes that fit both metric and imperial optical tables. Focusing a little bit more, to the third component of our FLIM kit, we have our FLIM data acquisition card, which is basically a TDC, so a time-to-digital converter for implementing the time-correlated single photon counting technique. This device card, this FLIM data acquisition card, that's the name we call it, is USB powered, and it yields, some specifications that perfectly, suits the application of fluorescence lifetime measurement. Indeed, what the card does for every photon that comes from our detector, for every digital photon that comes from our detector, we send a timestamp according to the TCSPC principle to the computer. Another feature that we implemented in our FLIM data acquisition card was to equip it with LEDs, LEDs that would, emit, let's say, blink at a proportional rate, at a rate proportional to the incoming signal. So let's say if we were to have a channel 3 which is not active, we would not see any light coming from the LEDs, while if the channel 1 was active, we can spot right away the fact that we have a signal on a certain, let's say, channel without the need of opening up our software. Together, in the same way that we shaped the case of the detector with the holes, we did the same, equipping the FLIM data acquisition card with some wings, that's what we call it, for securing the card to any type of surface or to any type of optical setup. Of course, as I mentioned, we have a fourth component in our kit. Besides the 3 hardware modules, we have a fourth component, which is basically the software. And for the data acquisition card concerning, let's say, single point time resolved application, we developed 3 different softwares, all of them are based out of Python. So basically, we have one card, but multiple Python-based software application. We have a simple, let's say, software for measuring the photon counts coming from our detector, some kind of an advanced potentiometers. Then we have a spectroscopy software, which is meant for time-resolved measurements, which I'll demo for you in a bit. And then we also developed recently a software for dealing with fluorescence correlation spectroscopy analysis. So all these softwares are available for free download for all the owners and users of our FLIM data card from our website. Allow me now to share the GUI of our software and live demo for you the spectroscopy software. So you see here, I am acquiring data from a laser that is pulsing at 40 megahertz. I am acquiring on just one channel, and I am acquiring a signal for 10 seconds. So the idea is that whenever I am starting the acquisition, you see I have the possibility of displaying the TCSPC profile, so my intensity decay profile, in a real-time manner, without the need, let's say, of waiting for a post-processing phase. Together with the acquisition, I can also export the data, and I can also export the data under the form of the time tagger, meaning that I can export individual time of arrival of single photons for, eventually performing a more in-depth post-processing analysis. Let's leave the export data on the side for the moment. What I wanted to show you is the capability of such a software to perform a phasor analysis, in real time. You see that after a proper calibration, I can jump onto my phasor plot in a matter of, let's say, seconds, and come up with, let's say, a result basically in a real-time manner. So this is the potentiality that we wanted to include in our FLIM kit, not only the hardware compact and, let's say, portable, but we wanted to push also the boundary and the envelope, providing a software solution capable, of being user-friendly and, most importantly, dedicated for the task, so fit for the job of measuring fluorescence lifetime. Let me go on into our, let's say, presentation, because recently we've been providing the FLIM kit with two setups, so coupled with two setups. One of the setup is a cuvette setup, is a cuvette-based system, and while a second setup we developed together with a Mexican company, Educaciencia, and is a setup meant for analyzing solid samples, contrarily to the cuvette where you would have, let's say, liquid samples. Let me tell you also that the FLIM kit, I'm gonna spoil a little bit because this will come into a dedicated webinar in the future. But let me tell you also that the FLIM kit can be coupled not only with single point optical setup, but also with imaging setup, and it's capable of performing a real FLIM, so fluorescence lifetime imaging microscopy type of analysis. Why is that? Because the FLIM card is capable also to be coupled with a dedicated software, which we call FLIM Imager, meant purely for FLIM type of analysis, actually FLIM phasors type of analysis. To show you a little bit more about the imaging capabilities, we decided also to develop some upgrade accessories that would work in conjunction to the FLIM kit for eventually being able to adjust and adapt the FLIM kit eventually, to other lasers and other detectors, like the FLIM upgrade we developed for the Bruker Ultima 2-photon excitation laser, which I'm showing you here. So you see in this type of upgrade, we are not using our detectors, not even our lasers, but we're using a PMT, which we digitize using some accessories. And then we are using a 2-photon laser source, which we are able, to digitize using our constant fraction discriminator. So you see that the FLIM kit not only has to be conceived as a, let's say, a closed solution, but also can be adapted and to other, let's say, type of FLIM setups. But now I'm gonna give the stage to our special guest of today's webinar, Professor Francesco Cardarelli, which is one of our collaborators, and he's an associate professor of applied physics at the Scuola Normale Superiore in Pisa. And I'll have him, talk about the application he was able to unlock thanks to our technology. So thank you, Francesco, for joining us. I'm gonna leave the stage to you.
Thank you. Thank you, Alessandro, for the kind introduction. Good afternoon, everyone. Thank you for inviting me to talk in this webinar. It's a pleasure to have the opportunity to talk about fluorescence lifetime and to talk about the impact that FLIM Starter Kit can have on this kind of applications. As Alessandro mentioned, my interest falls in the field of applied physics. I do my research at the National Enterprise for Nanoscience and Nanotechnology laboratory that Scuola Normale Superiore dedicates to applied physics. Here I established my research group, also thanks to an ERC grant that funded our research starting 2021. More in detail, I work in the field of nanomedicine. And in nanomedicine, I will build briefly a case study that demonstrates the potential of fluorescence lifetime analysis and the impact that the FLIM Starter Kit Alessandro developed can have. The drug you see on the screen in black and white is one of the most famous in nanomedicine, is Doxil, is nano-encapsulated doxorubicin. This is a picture from the patent 1995. And at that time, doxorubicin was meant to be dispersed in the aqueous core of the nanomedicine. You see this wonderful nanosystem. Doxorubicin is fluorescent. And today, by exploiting this intrinsic signal, and in particular by measuring its lifetime, we were able to discriminate that doxorubicin instead, within the same nanosystem, is present in 3 molecular conformations. free, crystallized, and a previously unknown one that is doxorubicin bound to the lipids of the nanosystem. Of course, using the phasor approach to fluorescence lifetime in a fit-free graphical manner, as Alessandro said, you can quantify the fractional intensities of these molecular species once you identify them. And thanks to the clever combination with some spectroscopic characterization, you can even measure the molar fractions of the same species. So you may understand the breakthrough that fluorescence lifetime analysis can introduce into the field of nanomedicine if 30 years after its invention and patenting, we have to update our view on the synthetic identity of doxil. As you are going to see in the next slide, on the left, you have how the researchers meant this nanosystem to be composed in 1995. On the right, we have our fluorescence lifetime analysis based picture today. But the breakthrough is real if these discoveries, if these basic observations are able to go out of the lab, to go out from basic research, going through all those technology readiness levels that you're going to see in a moment, from basic research towards the market. And this is the path we are doing together with Alessandro, with FLIM Labs. And of course, the Lifetime Starter Kit is crucial to do this, to move across these steps. And in a moment, you will see the FLIM Starter Kit on the bench of our laboratories at Nest in Pisa. And you recognize, of course, the components because Alessandro introduced them very well and very detailed. So the picosecond pulsar laser module, the SPAD detector, the TCSPC electronics, and of course, the sample holder you see on the bottom right. You see that sample holder is a cuvette because these projects started in cuvette. And the laser is flashed into the cuvette and excites the drug fluorescence lifetime is detected, phasor plotted, and then interpreted. You are going to see in a moment a movie showing you, demonstrating you that the measurement can be performed real time. So the laser is flashed. This is fluorescence from doxil. This is the phasor plot, giving you the fingerprint, the lifetime fingerprint of this drug. On this basis, you could compare drugs among them. You can do batch-to-batch analysis, drug leakage analysis, drug stability analysis, and so on. So to conclude, I would like to briefly point out that this kind of technology applied to nanomedicine is label-free. You're exploiting the intrinsic signal from the drug. But the FLIM Starter Kit is making this technology also sample manipulation-free, smart, fast, cost-effective, because the interpretation is, the measurement and the interpretation, as you could appreciate, is in real time and fully graphically and fit-free. And also, it started in cuvette, but why not the intrinsic versatility of any optical setup make us envision a bright future for this technology to move towards in vitro and why not in vivo applications. So with this, I conclude, and I thank you again, you for the attention, Alessandro, for inviting me to this webinar.
Thank you, Francesco, for the nice presentation and for your insight in using our kit in unlocking a new application in the pharmaceutical, let's say, sector. So I think this is all for today. So thank you all that you joined the webinar, and see you in the next webinar. So thank you, everybody.